Good morning, everyone. I forgot to turn my light on. Good morning. I hope you're all doing well. I am, under the circumstances, I'm doing quite well, I think. There's just a quick thing. There's a bit of lag today. I don't really know why. It seems like it's like 2.5 minutes of me between me changing what I change on my screen and it actually changing on YouTube. So if I'm a little bit slow to reply to comments and everything, that is at least a contributing reason as to why. I don't know. Welcome to Australia. Yeah, this week is so close to being such an exciting one. I think still it is exciting. I've made some much needed changes to what my plans were for how I was going to do things, and I think it's going quite well. Yeah. So I want to start off by just showing you all what I'm up to so far. So if I bring you over to my Jetson screen, I can start up the ROS network, and then we can pop over to the UI where I can refresh. And I currently do not have the robot itself turned on because, well, you'll see why soon. So I've got another sneaky little way to just tell the UI that the robot has been homed, and then I can actually start inputting things. Because you may remember before, I changed things around so that the robot cannot receive any commands unless it has been homed. That's fairly important because otherwise the robot will kind of do crazy things. And yeah, so I just have to go in the back end and tell things that it's been homed. And so I can do the usual inputs, like I control it with the space mouse in my hand over here. Or I can do the jogging, blah, blah, blah. But the new thing you might notice is that the pattern control is gone. I've gotten rid of that because I don't really care about that, to be honest. And I've instead replaced it with this juggle command. And you'll see it appears to be working. However, there's a few little issues with this. Let's ignore these console logs for now, for one. Talk about them a bit later. But for now, right now, I just want to show you what is working. So you can see that the position of the hand, it's really fast, which makes it kind of hard to see exactly what's going on. But the hand, if I just stop this, the hand is represented by these 3 orange dots that annoyingly disappear if I zoom too close into them. But that's, yeah, the radius of where the hand would be. And you can see it, if I make it juggle again, it's kind of hard to tell because it's so fast, but they do follow that path that is described here. But you'll notice that the robot is not tilting the way that it should be tilting. My plan here is for the orientations of the platform, of the hand specifically, I guess, to match the ball on the way in and out so that it can catch it nice and smooth. And you can see that's clearly not happening here. This is just purely flat. And in a little bit, we'll talk about why that's happening. But also, of note, in my opinion, I can change things about the pattern itself. So for example, we can change how far apart we're throwing. So if we bring it right in, and then it's just gonna be throwing straight up and down. Or we can increase that heaps and go super wide. But we can see here, I've made it too wide, so now these legs are getting too short. And this is why I really wanted the workspace to be shown in here, because what I can do is I can get rid of the robot and just show the centroid, and you can see this moving around. And I mean, if things were running a little bit more slowly, we should be able to see this leaving the workspace at some point. Although actually maybe we can't because of this workspace being the convex hull, when in reality it's kind of that umbrella shape that we talked about before. I still haven't gotten around to making this the concave hull or something similar. Notably as well, you may have noticed when I quickly showed that before that the centroid actually doesn't follow the path here, and that's intentional, and that's because the centroid that's shown here, this purple dot, is the centroid of the platform, whereas the hand is it has a bit of mechanical advantage, I guess. It's kind of like mechanically linked to the position of the centroid, but it's not at the position of the centroid. And we can see if we bring the robot back, it's a little bit too fast to really see clearly, I think, but you can see they're not at the same position, the purple and the orange dots. But yeah, so I can change the pattern around and do all sorts of cool things, like change how long I'm holding it for, how long I'm empty for, like the span that I'm going to cover, or that the robot will cover when it's full or when it's empty. And that should be really handy to help adjust the pattern to make it nice and smooth. So that's all working well. But the fact that I'm showing this on simulation and not on the real robot is probably an indication that it's not all working well. And part of an indication of that, like if I turn these info logs back on, we can see there's these, I guess technically they should be error logs, not info. But I've just been doing a lot of debugging, and these should not be here. This is a bad sign. And we'll talk about what these are a little bit more later. But yeah, so that's all working well. That's all good. But all is not happy in Jugglebot land. Well, all is not well, I guess. But before we go on to what's not working, I think it will make more sense if we talk about what's actually going on here. I'm just going to turn all this off so it's not distracting for me. There we go. Yeah, so what's actually going on here to let this do what you just saw? And the key part of it is that everything is state-based. Last week, I mentioned that I should be able to get Jugglebot throwing and catching, at least attempting to, this week. And in my mind, last week, I had the idea that I would just hard code the path, the whole path, and I would just tell it, you go here, you go here, you go here, you go here, and there'll be no way to change that. And I pretty quickly realized that while that would maybe get us closer to the first attempt, that's kind of a dead end because it doesn't lead anywhere. It just wouldn't work. If I hard coded that path every single time, I would have to like rerun everything with a different path set up. It would just be terrible. So instead, I've changed over to a state-based system, a state machine, if you will, where a state is a position, a velocity, and a time. And these states are the catches and the throws, usually, except for the very first one and maybe like the finishing state. All the other ones are a catch and a throw. So we can say, for example, we catch here at this position with this velocity at a given time. And then sometime later, we might throw from here at this position with this velocity at some time n+1. And this is a time n. And this is really, I think this is a really neat way to do this because it will open up some possibilities, which I'll talk about in just a sec. So the way that this works in the code is there's a node. Let me get rid of my drawings. We have a ROS node called hand state manager, and this is on GitHub if you want to check it out, which stores and updates a buffer of 3 states. I could probably do more to have a bit more like prediction in what's going on in the pattern, but for now, I think 3 should be fine. And these 3 states are the one that we just recently passed, which will make sense in a sec. State 1 is the one that we're currently en route to, and then state 2 is the next state. So for example, if we are just starting out and we're starting at the bottom of like the hold routine, we're starting right at the very bottom, this would be state 0. State 1 would be the next throw, so the ball is going to be coming out here, and we make a path that looks something like that. And then state 2 would be the catch on the other side, so that would be coming in with like this velocity. Yep. And yeah, right now, aside from the very, very first one, which is like right at the bottom, all of these just alternate between catching and throwing. And so in hand state manager, there is a method that basically like initializes the throw state and the catch state with the variables that I just showed in the UI. And it just saves those. Like, this is where we're throwing from, this is where we're catching from. And let's just alternate. That is not ideal, I think, but for now it works. My semi-long-term plan with this, let me get rid of me, is to have it so that the throw state is updated on the fly so that we can tell the robot, I want you to throw from here, and now I want you to throw from here, and now I want you to throw from here. Obviously, from here being like a state, so like position, velocity, time. And then the catch state would be based on the throw state because, of course, where we are catching from is dictated by physics, not by me or the robot or anything else. Wherever we've thrown from, that is going to dictate where we're catching from. So I shouldn't have to tell it where to catch. It should be able to figure that out by itself. And that's the sort of next plan once this very basic one works. There is a bit of an assumption here that we have to make for this to work, for now at least, which is that we have to assume that the throws and the catches happen on the same horizontal plane. If we don't make that assumption, then it makes things a lot more complicated with trying to figure out where we're actually catching from, because the parabola that the ball follows intersects with a lot of spaces that the hand can reach, and for simplicity's sake, I think it's just a lot easier just to say we're going to be catching at the same height that we're throwing from, because otherwise, like, how do you pick which of those points you should be catching from? Yeah, I think this is something that I should be improving at some point in the future, where I can say, okay, you should aim to be catching in the mid at the same position that you threw from, but if that will not work because it will make the motors move too fast or whatever, if it's a problem for whatever reason, then you can adjust to catch higher or lower. And like, I myself as a juggler do this. If I have made a particularly poorly timed throw, I might be catching it like up here, or I might be catching it down by like my waist. And that does help to correct for bad throws, basically, or collisions and that sort of thing. So that would be a useful thing to have, but for now, keep it simple. Yeah, so everything is state-based, and the way that this like buffer here works, where we only have 3 states at a time, is that as soon as the current time has passed the time of state n+1, we get rid of state n. So going back here, we had these 3 states. So whenever the time is past the time of state 1, we get rid of state 0, because that's now completely gone. And now state 1 becomes state 0, because that one is the one that we most recently passed. And then we calculate a new next state. Yeah, so that's relatively straightforward. And if you're interested in how that works, then I suggest checking out the hand state manager node on GitHub in the usual spot. So this is all well and good. We've got a bunch of states, but states are not really what the robot will actually use to move around, and it will instead use paths. So it needs to have an exact location at an exact time to follow. And the way that this works is we have Juggling Path Creator, which is another ROS node, and this receives the 3 states and then creates paths between them. The positions are actually surprisingly easy. So if we are told that we want to like catch at this state and then throw at this state, we need to figure out all of the positions that we need to be in on the way to that next state. And here I want to have a slight, brief, hopefully, tangent on Beziers, because Beziers are amazing. So if you may remember that Beziers are the types of curves that I'm using to describe like this path here. This is a cubic Bezier, which you will become very familiar with in the next couple minutes. But before I go into like the math behind these, I just want to give a brief explanation for why I'm using these. And it's partly because they are easy to differentiate, which is very helpful for me. If you remember your high school physics, you may remember that the derivative of the position is the velocity, and velocity is very important for me. That's why it's a big part of the state. So I care about position and velocity, and so being able to differentiate the position is super helpful. And as a little fun fact for you, if you take the derivative of a Bezier, you get another Bezier. It's just Beziers all the way down. And for why I've used a cubic Bezier, which is one that looks like this, that's because it allows me to have a smooth position, so that when we have this quadratic curve that the ball follows, we can make sure that this is tangential on both sides. Whereas like a lower order Bezier, like a quadratic Bezier, has one control point and looks like this, and we wouldn't be able to match that up with the parabola. There would always be like, this is going this way, this is going this way. You can't make those line up. So second order wouldn't work. Third order, which is what we have here, would work. Fourth order and higher would work again, but then you're just getting more complexity and it's just not needed. And very helpfully as well, this type of curve gives a good amount of control over the movement limits. So what this means for me is that wherever I set these control points, the curve for my purposes at least, the curve is always going to be inside of those control points, which is really helpful because it means I can set this lower limit to be within the workspace so that I know that wherever the robot actually goes, wherever the hand actually goes to, it's still going to be in its allowable space. So I find that to be somewhat helpful. Do they not just need to intersect at the throw catch points? Yes. Well, yes, intersection is very important. So if we had the quadratic that the ball is following and then a quadratic Bezier with the control points looking like this and the curve itself would look like that, this would work in the sense that the hand will be at the same location as the ball when it catches, but it means that the ball will be following, it'll be going like, no, 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 boom, and then it will all of a sudden jerk to follow the hand. And I don't know, I call this intuition, but from my juggling experience, you need to be smooth. Smoothness is very, very critical, especially when you're doing 3 balls, it's fine, you can kind of do whatever you want. But as you go higher up in the number of balls, you need to be smooth. Otherwise, it just doesn't work. You can't keep the balls in your hands that well, unless you're like fully grasping them, but you don't want to do that for other reasons. So yeah, smoothness is very important. But you are right that would work for a low number of balls, I would think. Or if you had some really good way of grasping the balls. Yeah, exactly. Yeah, the throws as well would be messy, to say the least, I would think. Yeah. These Beziers are also, importantly, super easy for computers to handle. And this is where I want to get into the math a little bit, but only a little bit, so bear with me. I think you'll all enjoy this, hopefully. Except for maybe this line. So the standard form of a Bezier equation, of a Bezier curve like this quadratic one, or cubic one that we've got here, looks like this, where P1, P2, P3, and P4 are these control points. And this is really cool because P1, P2, P3, and P4 can be any dimensional. They can be 1-dimensional, which wouldn't really make too much sense with this sort of curve. They can be 2-dimensional, like what they're shown here, 3-dimensional, like what I'm using, or further if you want to go crazy. And this equation just works. And t here is the only other variable, is between 0 and 1, and just represents how far along this curve we are. So t, assuming that everything is evenly spaced, why can't I erase? Assuming that everything is easily spaced, t 0.5 would be right in the middle here. T0 would be at P1, and T1 would be at P4. And so as you increase t, you're basically moving along this path. So this form is a little gross. I am not a huge fan of polynomial expressions like this. They're just kind of tedious to work with. But thankfully, with a little bit of algebra, we can, let me get rid of me as well so you can see that extra t cubed there, which is pretty important. Yeah, with a little bit of algebra, we can turn this into a matrix, and matrices are beautiful. Look at that, so much neater. And if you're curious about how this algebra works, or anything about Beziers, I strongly recommend checking this link. I've put this in the description to this live stream, not specifically the matrix part, I've just put the general link. But if you add like the hash matrix, you'll go to this derivation. But this page is so helpful. It's one of the only pages that I've like kept bookmarked on my like Jugglebot bookmark folder for the entire project. This is one of the longest standing links that I've saved for the entire. It's so helpful. It's whoever Pomax is, they've done a fantastic job of describing how Beziers work, and like literally anything about them that you would want to know. It's so good. Yeah. So what I have in my code is I've got a whole algorithm which is a little bit confusing, but it doesn't really matter for now. That decides on the spacing here. So these control points are dictated based on the geometry of the throw. So like the throw height, and I've also set, like one of the limits that I've set is like how far this distance is, and I can just choose that. That's one of the ones in the UI. So, and then based on the velocity, it chooses how far to the side, like P2, like how far out P2 and P3 are from P1 and P4. And so the control points are all decided kind of geometrically. I don't need to worry about those. This matrix is already decided, but what my other code that I'm not going to go into now deals with this t, and that just spaces this out. And that variable is called ppath, because I want to show you right now how easily computers can do this. This is the entire calculation for all of the positions along the Bezier curve here. So we have these t values is just grabbing each value in ppath, which again is just like the spacing of where I want to go. And then we turn that into a matrix so that it looks like this. And then we just multiply everything. So we've got the t matrix here. Oops. We've got the Bezier coefficients, which never change. They are always going to be the same values. And then the control points, which are dictated by the geometry. And this single line just calculates the whole thing for the entire curve. So we get out all of the positions for the entire curve. And that, I haven't actually timed it, but I have no doubts that it is super fast. So good, so clean, so easy. So, going back to the main problem at hand, how do we go from states to paths? Well, we receive the 3 states and we calculate the positions in the way that I've just shown. The orientations are fairly easy as well, where we basically get the start and end orientations from the velocities of the states. So for example, if we're throwing from here with this velocity and we're catching here and the ball will be moving at that velocity, then we can calculate these orientations. So we can calculate the angle here and the angle here. I did actually make a mistake with this when I was first going through it, and I only realized it yesterday, where we need to make sure that we're not actually matching these orientations, because when we're catching, we don't want the hand to be moving in the same way as the ball, right? We want the hand to be facing in the opposite direction. So thankfully, that's relatively easy to fix. Basically, if this orientation is negative at any point, we just flip it 180 degrees. Solved. And I can't undo my erase. That's annoying. Yeah, so if we have these orientations like this, then to get the orientation along our path, we basically just interpolate between them. So we might start like this, and then by the end, we're facing like this, which is the opposite of our catch orientation. And throughout the path, we just slowly move up from like here over to here. And that should be relatively straightforward. And we will explore this should soon. And once this is done, we send the full paths, so which is a list of position, orientation, and time, which is so frustrating that it's really hard to like separate in my head. I've got one state, which is position, velocity, and time, and then like a separate kind of state, which is position, orientation, and time. I need better words for these, but state is the only one that I can think of. Anyway, so the entire list of everything, like the entire path that's being followed, all of that is sent to the GUI so that we can display it in the GUI and like see where things will be moving to. And then only the next pose is sent to the hand inverse kinematics to like get the ball rolling for the robot. Oh, I'm blocking the camera again. Yeah, to get the robot moving. So just to describe that in a little bit more, like my reasoning behind that at least, here is a network diagram of the ROS network, or at least part of it. And we can see here, this is our juggling path creator, which is the node that we were just talking about. This spits out 2 things. One is a big list of all of the paths, of all of the poses and the times and everything that the robot will be following in the near future. So this represents this full path and like all of the positions and all of the orientations as well, everything, the whole kit and caboodle. This goes out to paths topic, where it then goes out off to the GUI to be plotted. And then it also, you can see this other arrow here, it returns just a single instance. So just the first line of this goes off to the hand pose topic, where it then goes off to the platform pose topic, and then so on to actually get the robot to move. I was kind of debating how I should be setting this up when I was first working on it, and my original plan was actually to have it so that the juggling path, this is really annoying that the eraser only sometimes works. My original plan was to have it so that the path creator would only return this big list of all of the poses and all of the times. And then I would take that into the hand inverse kinematics and find all of the hand inverse kinematics and then send those off and then do all of everything every single time. But I pretty quickly realized that if I'm going to be setting this up so that the states are changing dynamically, that will not work. I can't have the system computing like 500 calculations that it's then overriding as soon as we expect the ball to be landing somewhere slightly other than where we were expecting it to be landing before. So I think this should be a relatively efficient way to do it, where only just a single position is like sent down the computation line, because all of this involves computation. This stuff is just plotting, like that's, or just like showing it in the GUI, and that should be handled, I think, by my other computer where the GUI is being displayed. So this should be relatively efficient. However, I've done some things a little bit silly, which I'll explain in a sec. Thank you, Darkman. I appreciate the effort. So this all looks good, right? I mean, to me, it does. This seems good. It seems like it should work, but it doesn't. And maybe it's worth showing you what is happening when it doesn't work. So if we go over to my Jetson screen, what I was doing before to make it so that the rotations weren't in place is I would basically just figure out all of the orientations and then just set them all to be nothing, basically. Also, I've got to say, I love this VS Code thing where you can edit multiple lines at once. It is so, so good. So I have just turned all of the orientations back on so that the robot will be moving where it thinks it should be moving to keep those orientations the same. We've just got to wait for Colcon build, which I want to have a quick little mention of, because this takes about, I mean, you can see here, 21.7 seconds to build the ROS network, whatever it's doing. I don't actually really know. But that's such an annoying amount of time. It's like just enough time for me to want to focus on something else. And then I start focusing on the other thing, and then Colcon build is done. And it's so frustrating. Like yesterday, I must have done Colcon build like 100 or 200 times. And it's just enough time for me to want to do other things. It's frustrating. Anyway, so let's run the network and pop over to the GUI. And we will home things. All right, so let's refresh. Bring the robot back. And let's see what happens if we get it to follow the orientations. Yeah. This is why we do things in simulation land before doing them in real robot land. I have no idea what's going on with this. Not a clue. Yeah, it's a bit funky. But let's go back to this. So, what do I think is not working here? I think there's a few possible problems. The main one, I think, is that I've done a few critical things a little bit inefficiently. And that's particularly important because a lot of what is going on, well, some of what's going on here, which I'll show in just a second, is very sensitive to time. And if something is taking more time than it should, or more time than I'm expecting it to, then it can really mess up everything else. And that's what all of these errors are that we see, but I'll show those in a sec. So the main point of inefficiency, I think, is in the hand state. It's probably easier to just explain it here. So this is in the juggling, whatever it's called, juggling path creator node. And what is happening here is that every time it receives some hand states, so it knows where we just passed, where we're going to, and where we're going to after that. Every time it receives those, it recalculates both of the trajectories. That's a good question, James. I will talk about that in just a sec. So what's happening is that when we have a state here, like let's say that we have just in simulation, we've just caught and we're now like over here and we are on our way to throw again, then once we throw and we get a new set of states, it recalculates this path, even though it already had calculated this path as the next trajectory. And that's obviously super inefficient. It's basically calculating things way more often than it needs to. And this is like not a trivial thing either. This is like a full trajectory. This is probably one of the most complicated sets of calculations that my whole ROS network is doing. And I'm getting it to redo all of its work twice, essentially. And that's obviously not ideal. So I need to change that, because that's a silly way to do it. I was kind of hoping that it would just work. Like, I knew at the time when I was doing this, like, yeah, this feels dodgy, but like maybe things will be fast enough, but they're not. And the other thing is that when I said before here that to send off to the hand pose topic, we're just sending off a single like pose, and that's going off to start all the calculations. The way that I'm getting that pose is by comparing the time that we are currently at with all of the times in the path. So we can see our path, and this binary search for nearest pose thing, ChatGPT wrote this. I trust that it works. It seems pretty legit. I probably would have a hard time explaining, I think, to a beginner what was going on here, but it doesn't really matter. But suffice it to say, we're basically saying the time right now is, say, 10 seconds. And within our path, we have times from 8 seconds up to 12 seconds, for example. And so then this binary search thing basically says, okay, we're going from 8 to 12. We are currently at 10. So what position does that line up to? Because remember, we've got this big list of pos, vel, and time. And these go all the way down. And we're basically saying, okay, we are at time here. So which of these positions and velocities, or orientations actually rather at this point. See, it's so confusing. Which of these positions and orientations is the one that we want? And yeah, this is the part that's particularly sensitive to time, because I think what's happening is because I'm getting everything because I'm getting the earlier step to recalculate the trajectories more than they need to, it's taking too long, and the current time is outside of this list. So if the path is going from 8 to 12 seconds, the current time is like 13 seconds. And that is why we're getting all of these errors here. Well, not, I mean, I can label them however I want. As far as I'm concerned, they're errors where, let me stop them for a second. You can see it says current time is outside the path's time range. And something that makes this even harder to diagnose is that ROS uses nanoseconds, and I'm a human and I don't think in nanoseconds. So comparing like two 15-digit numbers, or whatever they are, it makes it so much more tedious, I think. Let's bring that back and go back to here. Yes, so both of those are, I think, silly ways to do it. I think, now, in hindsight. So, let's get rid of all this. And actually, before I get to my possible solutions for that, I just want to mention one other thing, is that something clearly wrong is happening with the orientations. Like, this business should not be happening. It should be facing the correct way. And part of the tricky thing with figuring out what's going on with these orientations is that whenever I attempt to debug it, me adding the messages that allow me to debug, so I'm like printing the rotation matrices and that sort of stuff, whenever I add those print statements, it slows things down even more, which further exacerbates the whole timing problem, which makes things tricky. So I have in mind a couple possible solutions for these, at least for the inefficiency part. Be more efficient. Namely, I don't want to be repeating calculations. And I am relatively new to the whole like DQ thing in Python, which basically lets you make a big list of items, and then if you want to, you can set the maximum length of that list, and then whenever you add a new one, it just gets rid of the last one by default. and you can add items in the front or at the end, and wherever you add them, it will just kind of shuffle everything else around, and it seems to work really, really quickly. And yeah, so I was having a think about how I could use this with the whole trajectory calculation and sending off just like the next position to the hand node. And I think I have a good way to do it, which is to grab the next pose from the list and then just remove it. So what I mean by this is if we look back here where we have, this is the big list of all of the poses that are in the next path. What I was doing before was, well, what I'm currently doing, I guess, is comparing the current time with all of the times in here to try to see which one matches up. But these are calculated with the intention of all of these positions being followed. So I'm thinking that maybe I can just take just the top one and then send just that off, and then use the whole DQ thing to just get rid of that. And then once that position has been sent off, then once the time is right, we get the next one and then send that off, and then so on, and just kind of split them off that way. And then when we create a new trajectory, rather than recalculating them every single time, we check if we've already calculated that one, and if we have, we don't do anything, and if we haven't, then we just tack it on to the end of this big list. And then this list will, hopefully, it shouldn't grow infinitely, because it should, as time goes by, we will be getting rid of these one at a time off the top, and then once we've like completed all of the ones for a particular path, then we will tack on the next path on the end. And so this should like grow in a large chunk at a very quick amount of time, and then just slowly shrink back down until it's ready to be pushed back again. Maybe, hopefully. Yes, and my solution for the orientations is just to sit down, spend some time, and just nut it out. I don't know what's going on there. I think part of the problem, which is really frustrating, is that the 3JS scene, which is the scene that's being used to like render things here, uses a different set of coordinate axes than what I've been using in my calculations. So there have been instances where the robot simulation moves and orients the way that it should, but the arrows are all screwed up in the plot. Like just like everything is correct except for these graphical arrows, which are not actually doing anything. They're just here for the purposes of us, just to see what's going on. But I think that might also be contributing to this, but clearly here something is going wrong. Like here the robot is actually tilted in the wrong direction, obviously. So I don't know what's going on there. I just need to spend some time to figure it out. Yeah. And another idea that I have in mind, which I didn't write here because I didn't think to, is along the lines of what James said before, which is to slow things down. And I haven't done this before with ROS, but as far as I can tell, there is a relatively well-built, inbuilt system for what they call simulation time, where I think you can just slow things down and just run the simulation more slowly. And that will obviously help a lot with seeing what's actually happening in this sort of graph. Yeah, I think that should be very, very helpful. I just need to look into how to actually do it. Yeah, there's one other thing that I would be remiss if I didn't mention, which is that time is so annoying to work with in ROS. For me at least, with someone, this is my first interaction with ROS time, because there's two types of time. You can have the built-in interfaces time, or you can have like the RCLPy time, and these don't play with each other nicely. If you have time for one thing being described with like one setup, I guess, one like structure, and then you have a different time object with this other structure, both of them are valid, but if you try to add them together or like do anything with them, it doesn't work. And you have to like convert them back and forth to make sure that they are the same so that they can actually be handled correctly. And that was many hours spent just scratching my head being like, what format is this time in and what format is this time in? And to be honest, I don't feel like I fully understand it yet, but things are working. That aspect of things are working now, as far as I can tell. So I don't know. It's tricky. Yeah. So my plan is yeah, just make the things more efficient and then just figure out what the hell is going on with the orientations. There was an interesting discussion actually on Zulip recently with Ulf. I'm not going to attempt to pronounce your last name. But where he was suggesting that we actually don't need to orient the robot where to like throw and catch. If we just have it be flat, then like move flat and just like with the right velocity, then it should still be able to throw. And like I tried this myself, like juggling with keeping my hands as flat as I possibly could. And I was very surprised at how well it worked. And I think that this actually has some merit, and it's possible that a future version of Jugglebot won't even have the physical ability to orient. But that will require changing the path planning algorithm a little bit, because right now I'm assuming that the balls are being thrown straight out of the hand rather than being thrown out at an angle, and that requires tilting the hands. And I really want to see this work because I know that it can, and I just need to figure out what is happening. Yeah, but it's possible that in the future we won't even be able to orient, which will be interesting. Yeah. I think that's pretty much everything. Yeah, it's been an interesting week. I feel like it's so close. On Wednesday, I was very hopeful that we would be able to have the first throw attempt live in the live stream. And I'm contemplating, even if I get the simulation to be like looking nice, I'm contemplating leaving the first attempt until next week's live stream, or just like having a random live stream at some point during the week when I'm ready to attempt to throw, and just having it on YouTube. We'll see how I feel as things are going. But yeah, I think I have faith that this will be solvable in less than a week. I'm sure it will be. And it's so close. So close. Yep. But just got to keep on keeping on. Yeah, if you have any thoughts or suggestions or anything about any of this, obviously, please do let me know, because I am all ears. And yeah, until next week. If you would like me to have a live, like, if you would be keen to participate in a live stream for the first throw attempts for Jugglebot, let me know in the comments, because that will incentivize me to do it. Otherwise, I might be tempted. I could see myself, depending on how I'm feeling at the time, I could see myself just being very uncertain as to whether or not it will work, because to be honest, I am. And I'll definitely film it, but we'll see how I'm feeling. Yeah. But I may be convinced, I think, to do it in a live stream. That could be fun. We'll see. The last bits are always the hardest. I've heard, I remember Stuff Made Here described it as integration hell. And I remember when I first heard him talk about that, I was like, it can't be that bad. You just, all the bits are working, just put them all together. But yes, no, it's not that simple. When things actually need to work, then you realize where all the other problems were in the little systems where they seem to be working in their own little isolated environment. But then when you actually bring them into the whole thing, it's like, oh, hang on. Time is important here. We can't just be super inefficient with everything. Yeah. But, that's part of the process. It's part of the process. Juggling as a human is not super easy either. It's taken a lot of practice. I'm certain that even still, if we go back to like the very start of Jugglebot's inception, like 2 years ago, whatever it was, I am positive it will be able to juggle 7 balls before I can comfortably juggle 7 balls. And I've been trying this actively for like at least 4 years. So I think all of this still considered, Jugglebot will still be faster than me, which I guess is something, I suppose. Maybe it's just more of a testament to how slow I am at learning. Maybe. Anyway, enough rambling. That's it for this week. I think there's not much else. So yeah, I hope you all had a good week, and I hope you all have a good weekend. I'm going to have a good weekend, going on a long bike ride. Should be fun. Yeah, until next week, have a good one. I'll see you then.